Okay, so this is part three to section 5.5. You'll notice I'm spending a little more time on this. It is, a little more important than 5.4 in the sense that 5.4 was, we're using everything in 5.4 here. And I want to make sure that everybody understands this. This is an important part of this. But anyway, so what I'm going to do now is I'm going to go through one more example of an indefinite integral, and then I'm going to start showing you how to evaluate definite integrals. So let's start with our example. So our example is the integral tangent x dx. And of course, if you see this on a quiz or an exam, first thing you're going to ask yourself is, do I know an antiderivative? Do I know something that if I take its derivative, I get tangent? You can sit here for a minute and try and figure it out. Nothing's going to give you tangent. If you take the derivative of tangent, you get secant squared. Derivative of secant is secant tangent. So nothing appears to be giving you tangent. So we're going to need to be a little more clever about this. I also can't right off the bat do a u substitution. If I try and do that, the goal is I want to pick a u that when I take its derivative, I get something else that appears in the integrand. And that doesn't happen here. So what I want is I want to rewrite this. And anytime I'm stuck with something with trig functions, it's always a good idea to go back to sines and cosines. So tangent of x is, of course, sine of x over cosine of x. Now, if I ask myself, okay, do I see something that when I take its, do I see something here and its derivative also? And the answer is yes. Derivative of sine is, so derivative of sine up here is cosine down here, or I could also have the derivative of cosine is negative sine. So it just depends on, I need to figure out which one to pick for u. So we're going to figure out what u, du, and dx is. So if we stop and think about it, one thing you might pick is you might pick u to be sine of x. And if you start thinking through this, and again, you can do this on a piece of paper as I'm talking about it and see that it's not going to work. But if you pick u equals sine of x, du will be cosine of x dx. You can see that doesn't appear down here or in the integrand at all. You have 1 over cosine of x dx. You don't have a cosine of x dx. So it looks like the best thing to pick is going to be cosine of x for u. Then du will be negative sine of x dx. I can solve this for dx, it's minus du divided by sine of x. All right, so now that I've gotten all that, and you can see here, for my du, I have a sine of x dx over here at du. So that looks good. So if I plug this all in, I'm going to get the integral. So sine of x I leave alone. Cosine of x is now my u. Dx is minus du over sine of x. And when I do some simplification, you can see this works because the signs cancel. I'm left with the integral negative du over u, which I'm going to write as minus the integral 1 over u du. And this is one that I know the antiderivative for. So if I look at this, so if I look at my chart, or if I ask myself, okay, what do I take the derivative of and get 1 over u? That one is going to be the natural log of the absolute value of u. And then don't forget my integration constant, plus c. Last step, of course, I don't want this in terms of u. I want it in terms of x. So this is ln of the absolute value of cosine of x plus a constant. And if you look in the book, this isn't the formula they give. So you'll remember that, I have a minus sign in front of the ln. So if I have, so anytime I have like a number in front of ln, any kind of constant, I can make it an exponent. So I'm going to go ahead and make this super obvious. This is ln of cosine of x to the minus 1 plus a constant. If you remember, 1 over cosine of x is secant x. So this is ln of the absolute value, secant x plus a constant. All right, so that's going to be the last example of the indefinite integrals. Now I'm going to show you how to deal with definite integrals. All right, so new page. Okay, so the problem we're dealing with is, I might have, so the definite integral. That's where I have, integration bounds. So for my definite integral, I'm going to have something that looks like this, a to b. And if I had something I'm going to be able to use u substitution for, this is going to look like f of g of x times g prime of x dx. And again, this is going to be a little more, I'm going to show you what's happening here generally, and then we'll do some examples where we see, what exactly I'm doing. So beforehand, I would let u equal to g of x, du is equal to g prime of x. Now we need to be careful here. So I'm going to plug this in. So remember, these bounds here are x values. But now that I'm changing variables, so x went from some number to some number, u's going to go from a different number. So right now I'm going to write this as x equals a and x equals b, just to remind myself that these are the x values. So when I do the u substitution, what I'm going to get now is, sorry, I'm missing a dx here on the right-hand side. So what I'm going to get is f of u, g prime of x dx is du. So this is now my integral. And I can integrate this, but when I do that, I have to remember that these bounds are for x. So there's one of two things I can do. So let's talk about let's talk about what I usually do, and I think what's best practice unless something's really complicated. So because I'm given these values of x here, I can also figure out what the values of u are. So to find u values for the indefinite integral, plug into the u substitution. So what I mean by that is, I can get, so let's call it u sub a. That's going to be g of a, and u sub b is going to be equal to g of b. And what this integral now looks like, and again, if this is not making any sense, where I'm going to go over a bunch of examples, it's fine. This is the integral from g of a to g of b, f of u du. So all this means is, I'm going to do my regular u substitution stuff, but now that it's a definite integral, I need to make sure that I change my bounds here because my integration variable no longer is x. My integration variable is now u. So these have to be u values here. All right. So that's one option. The other option, and I'm just going to write up. So that's one thing you can do. The other thing you can do, and I'll do an example. So when I do my first example, I'll do it both ways. So your second choice, so you integrate, and then substitute x back in for u. So substitute the u's out again. And so when we do that, what I mean when we do that is, in the previous problems, we've gone through, we found an antiderivative in terms of u, and we went back and we plugged in what things were in terms of x. So you don't have to do that for the the definite integral. Oh, sorry, didn't mean to do that. So you don't have to do that for the definite integral as long as you change your bounds here. So as long as you change your bounds in terms of u, you don't have to go back and substitute back in for x. But if in the second choice that you have here, you can go through, integrate, substitute back in for x, and then use x bound, and then use the bounds for x. So again, I'll do some examples. Sorry. I'll do some examples. And you'll see what all I'm talking about. So let me pull one up here. Okay. So we have the integral from 0 to 4, square root 2x plus 1 dx. So again, this is a u substitution. You can see that, there's only really one thing to pick here for the inside function. U is equal to 2x plus 1. Du is then 2 dx. So that gives me dx is 1/2 du. So going through and plugging this in, this is the integral from x equals 0 to x equals 4. The reason I'm writing that is now this is the square root of u du. And then I have a factor of 1/2 I'm missing. So dx is 1/2 du, so I'll plug that in. So now the problem is, again, I could integrate this, but I can't plug in these x values here. I cannot plug in x equals 0 and x equals 4 because it's not the same integral. So what I need to do is so let's call this, so I'm going to, in this case, I'm going to write this as u of x. So instead of writing u is equal to this thing, I'm going to write u of x is equal to this thing. The reason being is I'm going to look at u of 0 and u of 4. And whatever numbers I get there are going to be my new bounds for my integral. So this is going to be the integral square root of u, pull out a 1/2 du. So when I plug in 0 for x here, I get 1. And when I plug in 4, I get 2 times 4 plus 1 is equal to 9. So these are my two new bounds. This was the lower bound. This was the upper. So when I plug this in, I'm going to get the integral goes now from 1 to 9. And then I'm going to do the integration. And when I do this integration, I'm just going to use the reverse power rule. This is evaluated from 1 and 9. And so when I do this, so I'm going to have to make a new page here. So this is 1/2 u to the 3/2 divided by 3/2, evaluated at 1 and 9. So when I do this, so simplify this, I'm going to get 1/3 u to the 3/2 evaluated from 1 to 9. And then this is 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. Okay, so a couple ways you can go about evaluating this. So 9 to the 3/2. So 9 to the 1/2 is the square root of 9. So square root of 9. Square root of 9 is 3. So this is just 1/3 times 3 cubed minus 1/3. And then 1 to the 3/2 power is, of course, 1. So anytime you do any kind of power of 1, it ends up being 1. So then this is 9 minus 1/3. So this is 26 over 3. So it is. So that's what we get using that method. So let's evaluate what we get using the second method. So let me take a second and talk about just some things to watch here. So anytime I do a u substitution, if I'm going to do it this way, I need to change the bounds of my integral. I need to change these numbers. I'm going to have to plug in, remember I plugged them back in here. The way I'm about to show you, I don't have to do that, but it's a little more complicated. So let's check it out. So I have the integral, from 1 to 4, square root of, and I've already forgotten it, 2x plus 1 dx. And it's the same idea. So I'm going to let u equal 2x plus 1. Du will then be 2 dx. And dx is 1/2 du. So go through the same exact things. So I'll just do this real quick. This is the integral from x equals 1 to x equals 4. X equals 1 to x equals 4, 1/2 square root of u du. So what this ends up being, so again, this is 1/2 u to the 3/2 divided by 3/2 evaluated at x equals 1 and x equals 4. So separate these. But now I need to be careful. I can't plug in these values I can't plug in these x values in for u. So what I'm going to do here, this is 1/2, and I'm going to go back and plug in for x. 2x plus 1 to the 3/2 divided by 3/2. And since I'm evaluating at x equals 1 and x equals 4, and I have my function here is a function of x, I can use those bounds, and you can double check. So I'm going to leave this to you, but when you go through and do this, this ends up being 26/3, just like we saw using the first example, or using the first method. To be completely honest, of the two, I use the first method almost exclusively. It's almost, unless your function's really gross, it's not much of an advantage to go back and plug back in for x if you're doing a definite integral. Okay, so let's do another example. So, so let's add another page. So we have an example. We're going to do this integral, 1 to e ln of x divided by x dx. Sorry, it's ln of x divided by x dx. Okay, so again, we're doing u substitution this section. So it should be obvious when I'm going to do a u substitution. So when I'm looking at this, again, I have a choice. I can do u is equal to ln of x, u is equal to x, u is equal to 1/x, and that's about it. So if you go through those, you're going to see that, if you set u equal to ln of x, take a derivative, I get 1/x dx, and that appears here. So that looks to be the best thing to do here, because the derivative of ln of x is 1/x, and I have a 1/x in the integrand here. So then I get du is equal to 1/x dx, so dx is equal to x du. Yes. Okay, so now I'm going to do this, and let's go ahead and figure out what u of 1 and u of e are. So this is where I'm changing the bounds of my integral. So u of 1 is ln of 1, and remember ln of 1 is 0, any log of 1 is 0, and then ln of e, this is e to the 1, this is going to be 1 then. And so when I go through and I plug these back in, so this is going to be the integral, and I'm going to change my bounds now. Instead of 1 to e, it's 0 to 1. ln of x is my u divided by x, and dx, let me box it off, dx is now x du. So when I cancel these, let me use red for that just so it's not. Okay, so what I'm going to be left with is the integral from 0 to 1, u du. And I can do this pretty easily. U squared over 2, evaluated from 0 to 1. Don't have to worry about the constant because I'm doing a definite integral. This is 1 squared over 2 minus 0 squared over 2. This is 1/2. So you're welcome to go through and do it the other way, where you substitute back in for x and use the x bounds. You'll get the exact same thing. Okay, so those are all the examples I have for all the examples I have for u substitution. Last section of this is a section on symmetry. All right. So we have a section on symmetry. So symmetry deals with, so we have a couple definitions. So let f be continuous on some interval -a to a. So this is called a symmetric interval. So it is symmetric about the origin. So, you know, the positive and negative length sides have the same, you know, value there. So we say f is an even function. Excuse me. F is an even function if f of negative x is equal to f of x. B, f is an odd function if f of negative x is equal to negative f of x. So you've probably seen this before. I'm just redoing this because a lot of people forget this stuff. So even functions, you know, if I plug in negative value of x, I just get it's like I didn't do anything. Odd functions, if I plug in a negative value of x, it's like I pulled a factor of -1 out. And now we have these rules. So we're going to let f be continuous on -a to a again. Oh, sorry. And then we have these rules. If f is even, then the integral from -a to a, f of x is equal to 2 times the integral from 0 to a, f of x. Sorry, I forgot my dx's here, so I'm going to go back and fix those. So if f is even, then the integral from a to a, negative a to a, f of x dx is 2 times the integral from negative a to a, from 0 to a, f of x dx. Okay, so what this says, and so the reasoning behind this, the proof's not too bad. Let's look at something that is even. So just so you can see the reasoning behind it. So something that's even is x squared. And let's say I want to do the integral from, you know, these 2 points. Let's call this negative a and a. The idea is, you know, these 2 areas here on the left and the right are the same area. So instead of doing the whole integral, I can just do half the integral and multiply it by 2. And that's the reasoning behind this theorem or this rule. And again, the proof's not too hard. It's actually, if you can do it, that's pretty cool at this point. If f is odd, then the integral from negative a to a, f of x dx, this is going to be 0. And again, there's something that there's a similar reasoning if you look at the graphs. Let's do, oops, sorry. So so there are a couple of odd functions, but I think the easiest one to see is if we're going to do sine of x. So sine of x looks like this. So let's do the integral from here to here. So if you look at these, so what I'm interested in is this area and this area. And if you look at this, you know, these 2 areas are the same. One's positive, one's negative. So when I do this integral, I'm going to end up getting 0 there. And that's kind of the reason behind this. It's not a proof. It's just kind of a mnemonic for remembering this. So that'll be it for section 5.5. I will post these and make them available on YouTube. So if you have any questions about the material, feel free to email.